So hi everyone and welcome to this colloquium. We're very happy to have with Rod from CERN. He's going to tell us about looking at the dark matter in Axion Haloscopes. Nick got his PhD at MIT. He then went for a postdoc at Berkeley and is currently staff member at CERN. He's done a lot of work on dark matter, both model building and different ways to look at dark matter. He's also done a lot of work on effective field theory, which is the subject of our workshop this week. And even though this is a very mature subject, he was able to find some new sum rules and surprising results with respect to the and today is going to tell us about something completely different.
Thank you, Yao. Hello, everyone. Thank you all for coming today. What I'd like to use my time for is to tell you two different stories. The first of these is why there's so much excitement in the dark matter community these days about axions. This really originates from the fact in recent years, we've understood how to build experiments in the coming decades could cover what is the most well-motivated parameter space for axions. So that means we're in a position that if axions are the dark matter of our universe, we could well know that answer definitively in the coming decades. I think in and of itself is an extremely exciting statement. It's actually not the statement I'm really going to be focusing on entirely today. Secondly, what I want to take advantage of is that in order to get to the most interesting parts of the parameter space where we think axion dark matter might live, we're going to have to move down through many orders of magnitude of unexplored parameter space. What I want to think about is what else, heard that ringtone several times already. What I want to take advantage of is that as we dive deeper into the unknown, what else might we run into beyond just dark matter? And maybe not to overly romanticize it, but I think we've had many beautiful examples recently of what can be lurking out there when we look deeper than we ever have before. Of course, probably the most famous one of this is this beautiful image from JWST. To be much more concrete about the types of ideas I think you could run into as you're looking for dark matter, I'll focus on two specific suggestions, although I think these could be representative of a broader class. Firstly, you could have something that we dub the cosmic axion background, which are axions that are not dark matter, but were instead produced in the early universe and persist as a radiation background today, like the cosmic microwave background. Secondly, I'll describe to you how these same instruments that were built to look for axions would actually be sensitive to high-frequency gravitational waves if they pass through the instrument. So this is the second part of the talk. Again, I will review axions at the start, but I just want to give credit to my fantastic collaborators in these works. The first of this was done with Jeff True and Hitoshi Moriyama, and the second with Valerie Domke and Camilo Garcia-Solis. That's where I want to get to eventually, but let's step back and let me try and tell you about the story of axion dark matter. I appreciate that not everyone spends most of their waking hours thinking about dark matter, although I'm sure you've all heard some stories like this before, but let me just give you my own spin on how I justify spending so much of my time thinking about dark matter. So for me, our modern understanding of dark matter really dates back to the pioneering work of Vera Rubin and Kent Ford in 1970. What they were doing was they were studying our nearest neighbor in the universe, the Andromeda Galaxy, which is what I'm showing you here. And they were trying to study the orbital rotations of objects in the Andromeda Galaxy. Actually, they were studying regions of ionized hydrogen, to try and see if they orbited consistently with our theories of gravity, just thinking of this as a blown up version of the orbits of the planet in the solar system. While we may not know the exact matter distribution for all the baryons in the Andromeda Galaxy, one can still make a rough prediction for what the orbital velocity should be as a function of distance from the center of this object. In particular, as we start to move out beyond where we can see any matter by eye here, we would expect that the orbital velocity should be tending off towards zero in either direction. Of course, famously, and as I'm sure you're all aware, this is not at all what they observed. In fact, they actually found that the orbital velocities were plateauing to a roughly constant value of about 200 kilometers per second, well out beyond where we can see any clear matter associated with the Andromeda Galaxy. It was as if our understanding of where that matter distribution is completely wrong. There had to be some other type of matter in this object that wasn't tracing what we can see by eye. So of course, this is now just one of many different pieces of evidence we have that there has to be additional matter in the universe. Essentially, at all larger scales, we look beyond just galaxies. We see there has to be some additional component that we broadly call dark matter. Looks better on my laptop, but that's okay. So the idea is that we're now in a picture where this is such a quantitative field that we know that not only do we need this additional matter component, but it has to be the dominant matter component in our universe, making up at about 84%. And it will come as no shock to you, the field of particle theory has really coalesced around the idea that this dark matter just has to be an additional particle. Of course, there have been other ideas that have been pursued, but really the miracle of particle dark matter is there are models you can write down where you essentially just add a single new state to the standard model. Then all of these observations become consistent with our theories. Of course, there are some caveats to that, but broadly, this is the correct statement. This seems like a very satisfying picture. We need to add in some new particle. We had all these discrepancies and we can bring them into alignment. The challenges really begin when you start to ask, well, what do you mean by that particle? What exactly is it? So if you start thinking about, well, what properties define a particle, probably the first one that would come to mind is what is its mass? This is where I have to be honest and say, as a field, we're hideously ignorant as to what the mass of particle dark matter could be. I'm showing you the way that you traditionally measure particle mass on a ruler, and I'm putting up here the masses of the standard model states. And even if we extend that to include the known massive neutrinos, you can see that the range of masses we know about is vastly eclipsed by the range of masses where dark matter could live. This is just a subset of the possibilities. For example, you could have primordial black holes being much, much higher than this. There's a lot of parameter space to explore, and so we need to have additional tools to think about where we should focus. And for a long time, we've used analogies with some of the problems we have in the standard model that have identified maybe we want to look at the sort of mass ranges that are around the standard model. And of course, this is where the famous WIMPs, also sterile neutrinos, live. Of course, there's still a lot of activity in this space, but we've covered a lot of the most well-motivated candidates in that range, although there's a couple that we should still go after. Additionally, we could think about heavy dark matter. That's not a particularly well-explored parameter space that people have been thinking about recently. That's not what I want to focus on today. Instead, what I want to think about is what happens as we move to lighter and lighter dark matter. Now, because dark matter generates a potential that impacts the gravitational movement of states around us in the Milky Way, we know roughly how much mass density there is in dark matter around it. So if we then start reducing the mass of the individual dark matter particles, of course, we have to proportionally increase the number density to make up the observed matter density. So because of this, as we go to lighter and lighter masses, the number density is exploding, and eventually you'll reach a scenario where these states will start to exhibit collective phenomena and can really be thought about as behaving like a classical wave, which is really where we end up when we're thinking about these lighter dark matter masses. And from that perspective, it's maybe not so shocking that all of these instruments that have been looking for nuclear recalls, for instance, haven't seen anything yet, because instead it's some collective phenomena that would really be the way that dark matter would emerge that lives down at this light end. So there are many wave-like dark matter candidates. Today, I just want to focus on what is probably the most well-motivated of these, and this is the axion. It's going to be this A that's living in the Lagrangian here. There are many reasons that people focus on the axion, but what I really want to tell you about today is how well we could discover it if it's out there. And really our best bets at the moment for looking for an axion, the fact that we think it could couple to electromagnetism, that's what this F here is, through this dimension 5 operator that I've written. To denote just a trivial point, because this is a dimension 5 operator, unknown coupling constant that tells us how the axion talks to the standard model is going to have inverse mass dimension. And this will be relevant at a couple of times in the talk. This single interaction, as I said, it's our best bet at the moment for discovering an axion, and it actually can allow the axion to undergo various phenomena which will allow us to discover it. But probably the most important one when you're thinking about axion dark matter is the fact that if you take this term and then solve for the classical equations of motion of the electromagnetic fields, find that you get a correction to Maxwell's equations. Actually, you get 3 corrections. The one that the axion dark matter community really exploits is this single correction to the Ampere-Maxwell law I'm writing here. So in particular, what you can see sort of by analogy, that if you have a magnetic field, in the presence of the axion, you'll have some small oscillating effective current. If we can go out and measure very, very small or effects due to very, very small currents, then we could hope to detect an axion. So that's at least the intuition for how this operates. I'll come back in a couple of slides to tell you some more insight as to how you would actually hope to do this. Having said that, let me now lay out how we're doing and where we hope to be going in the future when it comes to looking for axions coupled to electromagnetism through this interaction here. Let me just lay out the parameter space. On the x-axis, I'm showing you the mass of the axion over 20 orders of magnitude. The fact that I'm showing you so many orders of magnitude is just a subset of the broader problem that we don't know what the mass of dark matter is. What I'm showing you on the y-axis is this unknown coupling constant between the axion and electromagnetism. Again, it has inverse mass dimension, which is what I'm showing you here. So axions are very challenging particles to discover, but they are not as challenging as this plot is representing at the moment. What I want to do in the coming slides is just to build up for you what we know about and where we hope to go on this particular parameter space. To begin with, one aspect that we know about axions is that regardless of whether or not they're dark matter, if they just exist as states in the spectrum of the universe, they cannot be too strongly coupled to electromagnetism. The reason for this is, if there was a strong coupling to electromagnetism, you could imagine producing these axions that are then relatively weakly coupled so they would fly out of compact objects like stars. Now, this could either then give rise to anomalous cooling of these objects, which we can constrain, or instead, could potentially put an LHC dipole magnet pointed at the sun, look for the axions flying in, converting back to a photon, and trying to discover it that way. That's exactly, for example, how the CAST experiment was recently decommissioned at CERN, was looking for axions. Either way, at this stage, we so far see no clear hints for the axions. So through a broad range of techniques that are basically of the variety I've told you about here, we can rule out the parameter space that I'm showing you up above. This is axions that are true strongly coupled to electromagnetism would be inconsistent with these measurements. That just gives us one boundary to the space. We can't live right up near the top. There's actually another boundary that I can put. That comes from now, if I assume that the axion is additionally dark matter, well, then this coupling to FF tilde allows the axion to decay to 2 photons. And at these high masses, that decay rate would be rapid enough that we could detect this. And what you would be looking for is, because this is a 2-body decay, you'd be looking for a photon line coming at half the dark matter mass, regions where you have large dark matter density. For example, if you just look at the energies here, we're looking at, say, keV up to 100 MeV. These are the sorts of energies where we have satellites that can look for exactly these types of lines, and this is where these constraints are coming from.
So the decay is slow enough so that it doesn't deplete.
You can check at roughly this point here, it would be about 10 orders of magnitude longer than the age of the universe. Only 1 in 10 to the 10 dark matter particles would have ever decayed. There's so much dark matter out there that that's observable.
I thought the bound was 10.
No, oh, well, good. I'll show you in 1 second one of these, but it's a great question, yeah. So to follow up on Carlos's question, also for those of you sharp enough to notice that I've identified one of these little islands down here in blue, I had a 2-fold reason for doing this. The first of them is purely self-serving. The actual island is a result of my own work. Just to give a flavor of what we're actually doing here, we were using the European Space Agency's XMM Newton telescope. We were looking actually for sterile neutrinos at the time, which is one of these other dark matter candidates I mentioned. So neutrinos are also predicted to undergo a 2-body decay involving a photon, so you can look for photon lines and try and constrain this. Constraints that we arrived are actually at around 10 to the 29 seconds. I'm showing you here. If you then translate that back into a GA gamma gamma, is exactly what gives rise to this island here. But this gives you a feeling for what these constraints are doing more broadly at that mass. So before I move on to talk about the rest of the parameter space, I just want to make a slight offhand comment about something that's interested me recently. And that is that whether or not the axion is the dark matter of our universe has an unbelievably enormous impact on this high mass end of the parameter space. Draw your attention, if, at this particular mass point here, the difference between these 2 constraints is about 7 orders of magnitude in this coupling. If you can turn this into the decay rate, it would mean that it's 14 orders of magnitude. It's decaying 14 orders of magnitude faster an axion up here than one is down there. Although this assumes that this is none of the dark matter, if I turn this around, this means that an axion living here couldn't make up more than 1 part in 10 to the 14 of the dark matter of our universe, an unbelievably strong constraint. So if you then start thinking, is there any way that these same couplings could produce axions in the early universe that you couldn't turn off? Indeed, there actually is. These same couplings would produce some fraction of dark matter and axions. If you push that line of thinking through, some work that I hope to have out soon with Kevin Langhoff and Nadav Mezgin, we've been able to show that you can extend the constraints on axions that aren't dark matter to these funny contours I'm showing you here. This is ongoing work, but I'd really be happy to talk about this offline if anyone's interested. So coming back to the primary theme, the focus now is that we've shown that you cannot live up here and you cannot live far to the right. So if axion dark matter exists, it has to be in this lower left portion of the plot that I'm showing you here. Of course, now I could go and speak to my experimental colleagues and say, please just cover as much of this white space as you can, because you might run into axion dark matter. That's one approach. I think it's also very helpful to go to them and say, actually, although it could potentially live anywhere, we have a best guess as to where we think the axion could live. One of the really exciting things about axions is not only could they be dark matter, could also solve one of the other problems that we have in the standard model. This is the famous strong CP problem. So in addition to this coupling here, if you had an axion that was coupled to the QCD analog, GG tilde, the axion can then dynamically relax theta QCD to explain why we seem to have such a small value of this in our universe. However, through this same coupling to QCD, the axion would also eventually pick up a potential and therefore a mass, which would relate its couplings to the size of its mass. We would end up with some sort of relationship that looks like this diagonal line I'm showing you here. Now, it's not a strict relationship because that coupling is to QCD, whereas what I'm showing you here is the coupling to electromagnetism. There's some UV model dependence, which would allow us to move around this line. Many of our best motivated models live right along here, like, for example, the famous KSVZ and DFSZ axions, which are the specific instances I'm showing you. So now we can go to our experimental colleagues and say, please cover as much of this diagonal line as you can. And you can see in some cases, it's many orders of magnitude below what we get from, for example, star emission bounds. So how are we doing in these searches at the moment? So broadly, these instruments that are looking for axion dark matter are called Axion Haloscopes. The reason for this is because they're looking for axions that make up the dark matter halo of our Milky Way. So you can see that if you have a dark matter axion that is around a micro EV, then we're doing very well. In particular, the instrument that is really leading the way here is ADMX. You can see that at the moment, it is cutting into the most exciting part of the parameter space for axion dark matter. And it's not impossible that any day now, we could expect a discovery of dark matter to come out of ADMX. So it's a very exciting time. However, we can't say with certain that that is really the correct mass of the axion. Various arguments that it could live essentially anywhere along this line here. So ideally, we'd want to have a number of different instruments that are tackling the different mass range that I'm showing you. You might notice that while we're doing reasonably well here, we are doing very poorly when it goes to lower masses. These instruments, like ABRA, which I was involved in, and SHAFT, are not yet getting below the star emission bounds. They made the additional extremely strong assumption that the axion is dark matter. It's a very non-trivial assumption, and yet they're not yet able to get below this bound here. Why am I showing these to you? Because these are proof of principle instruments. ABRA 10 centimeters is only about the size of a grapefruit. It's been a very small instrument. What we've been able to demonstrate is that instrument can get down to the theoretically predicted noise floor. This gives optimism that as we build bigger versions of these instruments, they should be able to scale rapidly. In fact, it's been shown that these types of instruments have a better volume scaling than the resonant cavity instruments like ADMX. You combine that insight with additional search strategies. Like technically, actually, these instruments operate as a broadband search for axion masses, but if you swap over to resonance strategies, which you can prove are more optimal, you can prove that they're optimal. The aggressive plan for the coming decades of the dark matter radio program, which is an upscaled version of ABRA or SHAFT, is to cover the entire parameter space I'm showing you here. Now, this is ambitious, but the experimentalists are confident that it can be achieved. Realistically, it will probably take a number of decades, but I think the fact that we have an idea now in existence that would allow us to cover these lower axion masses along the QCD line is a very exciting possibility. This is just one of the ideas that are being pursued in the literature.
Is it strange to just reach the QC line? So
Well, it's a resonant
exaggeration
it's a resonant instrument. It's a good question. It's a resonant instrument, so you determine how much time you spend at each mass. So they're just determining to spend enough time that they get down there. It's a choice. But the fact that they can even do this in a human lifetime, I think, is a very exciting possibility. Dark matter radio is just one of the many instruments that is being discussed at the moment, and I'm just showing you several more. Going forward, ADMX has plans to significantly extend their reach. There's ideas like the plasma haloscope. There's this other instrument, which has an acronym called BREAD, but fair enough. And there's a future version of CAST, which is called IAXO, which will also be able to extend the star emission bounds to cover some of the interesting QCD parameter space. So broadly, we have a number of instruments. And if an axion is the dark matter of our universe and one that solves the strong CP problem, it seems like we're in a very good position to answer that question in the coming decades. That's a very exciting possibility. But as I've told you earlier, it's not the only thing I wanted to tell you about today. The other topic I wanted to focus on is, in particular, if we look at dark matter radio, notice how many orders of magnitude they are going to have to move through of unexplored parameter space in order to get to where we really care about the QCD axion. The question that I've become interested in is, as we look deeper and deeper down, what else might we run into? So I've already laid this out to you before, but I want to describe to you two different types of signals that these instruments could run into. The first of these are axions that are not dark matter axions. These are instead axions that were produced in the early universe and remain relativistic today and just exist as a background like the CMB, something we dub the cosmic axion background. And secondly, I'll tell you about how a completely different type of wave passing through these instruments, in particular high-frequency gravitational waves, could deposit a signal that you could detect. So that's the goal. I have one more warm-up comment that I want to make, and that is that although I've laid out for you the parameter space for where these various instruments hope to cover, other than saying some simple words about a modification to Maxwell's equations, I've given you no real insight into how these instruments operate. Let me just spend a couple of slides describing to you how one of these instruments operates, sort of a version of dark matter radio. So then you'll have some intuition when we go to these other signals, especially the gravitational wave, you could still imagine a detection could be made. Good, so just to flash this once more, the main idea that all of these haloscopes are relying upon is this single modification to the Maxwell's equations we have here. As I mentioned, this term actually induces three different corrections, but it's this single one that dominates. The fact that in the presence of a magnetic field, if you have an axion, you give rise to some electromagnetic effect you could go and search for. So step one is you need a magnet. There's various different magnet topologies that are being pursued in the literature, so please don't be too attached to what I'm showing you here. This is the toroidal geometry. There's various other ideas that are being explored, but this is just one concrete one to discuss. Of course, it's not just enough for the experimentalist to build a magnet to see something. There's a second key ingredient, and that's axion dark matter. You need to have an axion, which I'm just cartoonishly drawing as this wave oscillating through the experiment, to be present in order to have a signal. And then through the correction to Maxwell's equation I showed you, if you have a toroidal magnetic field, the axion will give rise to a toroidal current that will be oscillating back and forth in sign because the axion field itself is oscillating back and forth in sign. This will then give rise to an effect you can search for. If you remember your right-hand rule, this oscillating current will give rise to an oscillating magnetic field in the center of this torus. At least ideally, there should be no large component of the magnetic field. Of course, there are experimental realities associated with that, but for the moment, we just imagine that only the axion induces a magnetic field in the center. If one then puts a pickup loop in and reads out the current from that, you can measure the oscillating flux you would have in the center of this. You can calculate this roughly. It will have the parametric form I'm showing you there. It's proportional to GA gamma gamma, as it must. The derivative, because the axion's a pseudo-Goldstone boson, is proportional to this magnetic field, and then also the volume. And the fact that it just scales linearly with the volume is actually an enhanced sensitivity over something like ADMX, helpful for this. But then the idea is you would measure some time series of this flux, the Fourier transform of that, and you would see some spike at a frequency corresponding to the mass of the axion, if that is what is the dark matter of the universe. This is at a very cartoonish level how these instruments operate. Notice at no point in that discussion did I require the axion passing through this instrument to be non-relativistic. If I had a relativistic axion passing through the instrument, it would still elicit a response. So this is what takes me to this first topic, the cosmic axion background, which again was work done in collaboration with Jeff Draw and Hitoshi Murayama. So I'll go into a lot of the specifics about the CAB and tell you about some of the ideas I'm really excited at the moment. But ultimately, if you just take one takeaway message from this section of the talk, that would be fantastic, is this one here. I want to answer for you whether it's even remotely possible these sorts of instruments, as they dive towards where they think dark matter could run into instead a cosmic axion background. Let me start by laying out the landscape. As you can gather, I like these types of plots. So what we're going to be looking at here is, instead of previously I looked at the dark matter landscape, now I'm looking at the landscape for these relativistic cosmic axions. So because they're relativistic, mass is not the relevant parameter for dictating the phenomenology. It's the energy that will dictate at what frequency the responses that are elicited in the instrument. I'm showing you the frequency on the x-axis at various values for where we're already searching for dark matter, because there you can match the mass there is what gives rise to the frequency of the response you induce. So I'm just showing you ranges that are being searched for by dark matter radio, resonant cavity instruments, this plasma haloscope I mentioned, and again, this is just a subset of the many instruments we're pursuing. What am I showing you on the y-axis? I'm now showing you something that we didn't have to talk about for axion dark matter. As I mentioned earlier, Dark matter gives rise to a potential that impacts the evolution of stars around us in the Milky Way. From this, we can infer how much dark matter energy density there is. It's not a free parameter. For the cosmic axion background, it 100% is. I need to specify for you how much energy density there is at a given frequency of this relativistic axion. That's what this omega A is quantifying. Technically, it's defined by what's in this orange box here. For those of you who are familiar with the stochastic gravitational wave background, it's actually defined in the exact same way as what I'm showing. One comment, of course, you can ask, previously I showed you GA gamma gamma on the y-axis here. That has to play some role in the story. I'm just not showing you it on the plot at the moment. I'll come back to GA gamma gamma in a couple of slides. So even if you're very familiar with the stochastic gravitational wave literature, let me just give you some intuition for what these values on the y-axis correspond to. So if you had an energy density in the cosmic axion background that was equal to the energy density in the cosmic microwave background, you would have to live somewhere around this gray dashed line I'm showing you here. Of course, you would also live in a universe that is different to our own, because that is completely inconsistent with values of delta N effective that we've measured, for instance. However, this gives you some intuition that maybe the most exciting part of the parameter space would be to live not too far below the gray line here that I'm showing you. Because if you did, not only might you be able to see a signal with the types of ideas I'm telling you about today, in the near-term future, you might also see a modification to cosmology through, for example, a non-zero delta N effective. So that lays out the axes. Now let me tell you what the CAB could actually look like. And I think the case that comes to mind first, at least it does for me, is the case of a thermal cosmic axion background, sort of the closest analogy to the CMB that we can come up with. The idea here is that if the strength of the coupling strength of the axion to the standard model is sufficiently strong, and depending upon the reheat temperature, there is a possibility that the axion was in thermal equilibrium with the standard model at high temperatures. Eventually, this would decouple, and then you would have this black body distribution of axions that would just redshift until today. And very similar to the CMB, it would actually be peaked at microwaves or at about milli-EVs. Now, the exact peak location and the height of this distribution depends upon specifically when this thermal CAB decoupled. However, on this plot of many logarithmic axes, you can't actually move this around too much. You would expect it to live roughly around here. For me, I think this is the most exciting candidate to go after. You can imagine many different scenarios where the axion might have been in thermal equilibrium in the early universe. And so because of this, this would be a very exciting possibility to search for. However, let me be honest, what I'm going to tell you about now is going to get us nowhere near thermal CAB, which is a bit disappointing, but it is what it is. And I'll come back towards the end of this section to describe to you how we can think about why this won't be able to get us to the thermal CAB, and also to think about how a different type of experiment may actually be able to get there. But that's something that I'll put off for the moment. Next, I want to tell you about other possibilities, ones that these ideas could actually detect. Just let me quickly flash a couple here. What I'm trying to make, I'll run through these, but the point I'm really just trying to make, there are many different ways we can imagine producing relativistic axions. This is not at all meant to be exhaustive. Just to give you a couple, because of course the axion is the pseudo-Goldstone boson of some U1 PQ symmetry, when that's broken, we can expect cosmic strings to be generated that emit axions. This is a very active area of exploration, but the broad picture is that we expect roughly a scale invariant distribution of axions to be emitted. You could imagine such a distribution cutting through this here. You'd also imagine that there was some scalar in the early universe that's displaced from its minima. When it begins to oscillate, if it couples to the axion, it could go through the phenomena of parametric resonance and produce a roughly Gaussian spectrum of axions I'm showing you here. Just a note, bound requires you to have an integrated energy density that satisfies delta N effective. So you can, at individual points, pick up above this. But if you really want to get significantly above this delta N effective bound, what you need is some way of producing relativistic axions in the late universe. There are various possible ways that have been discussed in the literature. One simple one to note is, just as I discussed earlier, dark matter might decay to 2 photons. Maybe dark matter decays to 2 axions. If it does this, then you could produce very large energy densities of axions, probably what I'm showing you here. Just to be upfront, I'm actually lying to you a bit about this story. There's quite a few subtleties involved in this decay I'd be very happy to talk about, but roughly such a picture can hold, but it's not exactly as I'm telling you here. So now let me turn towards the question of detection. If such relativistic axions exist, how could we hope to see them at these types of dark matter instruments that I told you about earlier on? And to begin with, I think the following qualitative observation is a useful one. I was telling you earlier on that we know how much energy density there is in dark matter. But then as we change the mass of dark matter, we change whether it behaves like a gas of particles, this is the case of a WIMP, or whether it behaves like a classical wave. This is exactly what axions do. You can ask these same questions for any bosonic energy density. For the CAB, you can run the calculation. It turns out that if you live to the left of this dotted line I'm showing you here, you should eventually start to behave qualitatively like a classical wave. Whereas if you live to the right, instead you're just behaving like a gas of individual axions. But then if I'm going after these lower frequency axions, which I'm telling you is what I'm going to focus on, I really can think about the CAB as operating again like a classical wave. Which is very convenient because this initial detection language that I had, this coherent effect that's induced in this toroidal magnetic field, carries over to this scenario. With that said, now let me try and make this picture more quantitative so we can estimate whether or not you could ever hope to see something like the CAB. The idea is that in this regime, it's behaving like a classical wave. You can think about it as sort of a combination of individual particles that are each oscillating along some frequency is drawn from this distribution of frequencies I showed you on the previous slide, for example, the thermal distribution or the broad string distribution. Otherwise, there's no reason to expect these states to be phase coherent, but for each one of them, we combine together these random phases. With this picture in mind, I can actually now start to Monte Carlo or generate a simulation of what the axion field should look like in the time domain. Let me start by focusing on what that would look like for dark matter. Because of the combination of these random phases, there is some statistical uncertainty on exactly what the amplitude of these oscillations will be. So in these three different colors, I'm showing you three realizations of this. But what there is no uncertainty about between these cases is the extreme coherence of the oscillation. Note that in all cases, they are very, very regular. And the reason for this is that all the frequencies I'm drawing from here are almost at the exact same value, the dark matter mass. Again, of course, what is controlling the frequency here is the energy of the state. For a non-relativistic state, most of the energy is right at the mass, up to small velocity correction. The cosmic background, however, while there is this statistical variability between the random phases, you can see that the oscillations are not at all as coherent as a function of time. You can see that there's movement all over the place, consistent with the fact that we've added together a number of qualitatively different frequencies. One can start to study these distributions in the time domain, but especially when you're looking at something like this, it becomes challenging. I think the picture becomes much more simple if we Fourier transform and move to the frequency domain. If I try and study dark matter and a CAB on an equivalent plot, for example, I'm showing you frequency in nano eV here. Initially, what I would see for dark matter would just look like a delta function at its mass. I need, in fact, to zoom in by a factor of 1,000,000 before I can resolve the axion actually has a finite width, which is what I'm showing you here, which comes from the fact that while the particle is non-relativistic, it's not exactly at rest. You know that the dark matter is moving in the halo of the Milky Way at a speed of about 10 to the minus 3 in natural unit. Cosmic axions, however, I didn't need to zoom in at all. You can see that there is this very broad distribution without any magnification that's shown here. So before I even go on to tell you about whether this is detectable, let me just keep track of this because it's going to be a very important point. This is really zooming in on what is one of the fundamental differences between these two types of signals. I'm going to encapsulate it using what I call a Q factor for these distributions, which is a dimensionless measure of the inverse width. The narrower the distribution, the larger the Q factor. For dark matter, I can compute that this Q factor should qualitatively be about 10 to the 6. It's controlled by V squared. Whereas for the CAB, of course, the exact width will depend upon the specific candidate I have under investigation, but the width should be order 1. So because, I mean, this is a very qualitative difference, you can already begin to think about how this would show up in your instrument. For an experiment like ADMX, they're really looking for a spike in the frequency domain, right at the unknown mass of dark matter. The CAB, however, you were depositing power over a broad range of frequencies. So actually, as I was realizing this, I went back and read how exactly do ADMX do their data analysis. Step 1, when they have their data, smooth it out, track the smooth component, and never save it to disk. If there is any evidence for a CAB in ADMX's data, it is currently in the trash. That's a bit unfortunate, but I've been working with the ADMX collaboration to come up with an idea how you could actually tease this out without throwing out any signal you would have at step 1. It's certainly possible, but it's not being done at the moment. Because it is quite a qualitatively different signal you're looking for, deposited over to many frequencies rather than just this narrow spike. Before you can even convince the experimentalist to go and look for something, you better convince them that this is actually detectable. So let me now turn to that question. And I think the easiest way to understand the detectability of this candidate, of axions in general, is just to compute how much power is in this field that I could hope to pull out with my experiment. The way that I compute this is by calculating something that is called a power spectral density, a measure of how much power is in this object at a given frequency. So I can't just compute, it's not really useful to compute the power spectral density of the axion field. I can't pull power out of the axion field directly. There are two corrections to that simple picture. Of course, the axion we know is only very weakly coupled to the standard model, controlled by this GA gamma gamma, so I have to have that in there. And of course, the axions are pseudo-Goldstone boson, so there must be some derivative in this interaction as well. So I calculate the power spectral density of that combination. I find the form that I'm showing you on the slide here. I think intuitively, it depends on the coupling squared. It also depends on how much energy density is in the axion field itself. That's going to control how much energy I can pull out of it. And it depends upon where that energy is distributed as a function of frequency. The other factors are maybe not immediately obvious, but come out of the detailed calculation. What one can do now is just take various distributions for what the COB could look like and try and see whether this is a detectable amount of power. Just in the spirit of keeping this somewhat qualitatively, although I do want to give you an insight as to how detectable this is, other than go case by case, I can actually get rid of this probability distribution, which is a bit challenging to do with otherwise, qualitatively replace it with this Q factor I mentioned earlier on, and then an inverse mean frequency to make up the dimension. Why is it sensible to replace the probability distribution with this Q factor? Well, if you recall earlier, the Q factor measures how narrow the distribution is. P of omega is still a probability distribution. PDFs have to integrate to 1. In a very narrow distribution, the value of that distribution must be very high. You can check that it actually scales linearly, so I'm showing you a correct scaling here. What's useful about the derivation I've just gone through, though, that at no time did I say I'm talking about the CAB or dark matter. I'm just talking about getting power out of an axion field. I can actually use this expression for both dark matter and for the CAB. So one way to get an estimate for how sensitive an experiment should be to the CAB, I know what dark matter powers these instruments are sensitive to. I can say that the CAB will be detectable if it deposits an amount of power that is equal to dark matter. This is, of course, a very rough statement. I'll say some words on corrections to this shortly. At least this will give us a rough benchmark for how detectable the CAB should be. This is a simple exercise to go through. Just put in all the values for dark matter, put in all the values for the CAB, equate them together, and account for the fact that you're looking over a number of frequency bins. You end up with the expression I'm showing you in the orange box here. To focus, what I'm imagining here is that I have a very strongly coupled CAB, so that its coupling is up near these star emission bounds that I told you earlier on. And I can ask the question, what energy densities in these relativistic axions would actually be detectable? So I want to probe as small a value of this as possible. There are two challenges in the way of getting to small values. Energy density is much smaller than dark matter. So if I want to deposit the same amount of power, that is not a good start. Secondly, it's a signal that is much less coherent, that ultimately when you work this through, it turns out to hurt your sensitivity to this type of a signal. What you can win, however, if there is a strongly coupled CAB in our universe, as we start to get many, many, many orders of magnitude below these star emission bounds I told you about earlier on, this factor can easily overcome the challenges that are represented by these. This is a very rough estimate I've put you through here to let you know if you actually sit down and compute what exact response would a CAB elicit in these various instruments, you can confirm this parametric scaling just up to some order 1 numerical prefactor. Now let me go back to this scenario, and again, envisioning a case where the CAB is as strongly coupled as possible, I can just take experiments, use this expression I had on the previous slide, and just tell you what energy densities they would be sensitive to. Let me do this straight away. In the solid curves here, I'm showing you what the reach would be for ADMX and Haystack. And then in the dashed, I'm showing you future instruments like Mad Max and dark matter radio. So of course, these are not coconuts to coconuts. You can't compare them directly. But if you look at this, I think there's two immediate takeaways you should have from this plot. The first of these is that if ADMX can see anything at the moment, it's only going to be one of these late universe production mechanisms. It is not yet sensitive, even in this optimistic scenario, to get below delta N effective bound. Dark matter radio, however, will get down below this by orders of magnitude. There is every possibility that if there is a strongly coupled CAB at the location of the Earth, dark matter radio could run into this as they're looking for dark matter. That was the main takeaway I wanted you to have from this section. Let me just end on a couple of other questions that this plot has raised for me that I'm quite interested in at the moment. First of these is that I'm only focusing on couplings to electromagnetism in this talk, but please don't have the impression that's our only idea for how to search for axion. Actually, there's a broad program of looking for axions through nuclear couplings, for example, exploiting analogies to NMR-based techniques. Actually, it turns out that these sorts of ideas should be very sensitive to a cosmic axion background. But actually, as my collaborators and I have been digging into this, we've even found some new effects in the case of dark matter that have been overlooked previously. This is a very interesting story in its own right, but not one I'll tell you today. I think the most pressing aspect of this is how pessimistic the detection of the thermal CAB appears from the plot I'm showing you here. I'm being as optimistic as possible about the detectability of this scenario. I'm showing you an instrument that doesn't even exist yet, but we hope will in the coming decades. And even then, that is orders of magnitude away from probably this most exciting candidate that I'm showing you here. But I think if you look at this plot for a moment, it's maybe not too shocking. And the argument I'm about to give you, I appreciate, is somewhat hand-waving. If you look at the thermal CAB, it is really living in the regime where you should think about it as a gas of axions. It's not really exhibiting the sort of collective phenomena over here we would expect, where we would expect a wave-like behavior. At max, however, is looking for wave-like dark matter. Maybe it's not too shocking that an instrument that's looking for a wave isn't going to be very good at looking for individual particles. Now that we realize that the thermal CAB is really behaving like a gas of axions, you can start to think, well, do we know of ways to detect gases of axions? We do. I actually told you about one of these earlier in the talk. This is exactly what CAST does. Looking for individual axions produced in the sun, coming in, converting in a magnetic field, producing a photon we detect. But could we build a version of CAST that instead of looking for X-ray photons, which is what the axions produce because they're coming from the core of the sun, we look for microwave photons, this milli-eV value I'm showing you here. And this is very much preliminary work. My collaborators and I think that you absolutely should be able to build such an instrument. And I'm currently thinking about this with Jeff Traw, Matt Parl, and Ben Safdie. Our current projections, although this is highly preliminary, is that if a thermal CAB exists, we could build an instrument that could probe it if it couples to electromagnetism in this parameter range here, which even covers some of the QCD parameter space if you do some tricks. I'd be very happy to talk about this, but this is very much work in progress. So stepping back from those real details here, again, the one takeaway I hope you can have from this, that sure, we may need to be somewhat optimistic, but if relativistic axions were produced in the early universe, dark matter radio absolutely could run into them as they're looking for dark matter, but they should keep that possibility in mind. That's going to end my discussion of the CAB. What I want to turn to now is a completely different type of wave that might pass through these instruments that could also elicit a response. This is the idea that these instruments could also be sensitive to high-frequency gravitational waves. So again, I'll go into some of the specifics, but there's one takeaway you have from this section is hopefully some intuition as to why you can even think about an Axion Haloscope as a gravitational wave telescope. Let me just try and address this right off the bat. The starting point, if we want to understand the interaction between electromagnetism and a gravitational wave, we look at the action for electromagnetism in curved space. What does the curved space look like when we're describing a gravitational wave? Well, our usual picture is we just have some flat space. And the gravitational wave induces a very, very, very small correction to this. I really do mean extremely small. The size of this correction is controlled by what is commonly called the strain. For example, where LIGO was able to see something was when they were at a strain sensitivity of about 10 to the minus 22. So very, very small numbers. Because we're usually happy to drop terms that are order 10 to the minus 44, we can drop higher order corrections when we're substituting this in. And just being qualitative, hopefully you can see that if you substitute this metric into the action here, 0th order, what you will recover is just a classical electromagnetism in flat space. But at leading order or first order in H, we'll find terms that are qualitatively of the form HF squared. Being very qualitative, I do not literally mean the trace of H here. I'm just saying there are terms of order H and terms of order F squared. I'll come to the more accurate calculation in a few slides. Then I can draw an analogy, maybe strained, but an analogy nonetheless, between these sorts of HF squared terms and the exact type of operator we've been studying in the talk so far, this GA gamma gamma A FF tilde. Recall GA gamma gamma has inverse mass dimension. A is a scalar, so it has unit mass dimension. So together, this is a dimensionless quantity that plays the role of the strain. And then FF tilde is none other than F squared. Of course, that's not correct, but at least at some level, what you can see, if you have some electromagnetic field, just as the axion will induce an electromagnetic response, gravitational wave could also induce electromagnetic response. This is the idea here. And of course, let me be clear, the idea that you could have electromagnetism interacting with a gravitational wave is not one that was discovered in 2022. A very old idea that goes back to Gershonstein in the 1960s. Actually, a lot of aspects of this physics are still to be worked out, and I'll tell you about some of these today. So I will not go through the complete calculation of how the gravitational wave interacts with this system, although I'll give you some intuition for this. Nonetheless, I'd like to leave you with just some sense for how you could even imagine these instruments as being sensitive to gravitational wave. So to do this, I'm going to push this analogy between these two terms a little bit too far. I'm going to imagine that ff tilde is literally f squared, so then say I'll be sensitive to gravitational wave strains at the values of Ga gamma gamma times A that I've probed at Axion Haloscopes. That's exactly what I'm saying here. Then I can put in specific values for these. Of course, the axion's an oscillating field, so on average its value is 0, but it has an RMS value of the square root of the density over its mass. And then you can also rewrite the coupling as is conventionally done in terms of the decay constant up to an electromagnetic fine structure constant and a factor of 2 pi. Now, because of this, if I want to know what strain sensitivities I have to look at various instruments that will look for axions, look at the frequencies they considered, that will give me the value of M, and then look at what values of Ga gamma gamma they were able to probe, that will give me the FA. So you can do this case by case with the various instruments, and that's an exercise one can sit down and go through. However, know where all of these experiments are heading. Every single one of these Axion Haloscopes wants to get to the QCD axion line. And as I mentioned to you earlier, the defining property of the QCD axion line is that there's a relationship between the mass of the axion and its coupling strength. That relationship is controlled by the equivalent quantities for the pion. So for a QCD axion sensitivity, I can replace MAFA with M pi F pi, what I'm showing you here. What I've achieved at this stage is by saying that an instrument that is sensitive to the QCD axion, I can write its expected strain sensitivity entirely in terms of numbers that I know the value for. So I can just substitute this in, and I get 10 to the minus 22.
Awesome.
I hope you were impressed by this. Thank you, Carlos. I really appreciate that response. I was very happy when this number first came out because this is the strain sensitivities that LIGO achieved. And in some senses, I think this is a fantastic result that we're sensitive to such small strains. However, let me be honest, I wish we were sensitive to even smaller. And the reason for that is because the most interesting candidates we have for high frequency gravitational waves are signals that were produced in the early universe. For example, if there was some very high temperature phase transition, this could produce high frequency gravitational waves. However, anything coming from the early universe that behaves like radiation is still subject to these delta and effective bounds that I said that the CAB is subject to. So you can sit down and compute any gravitational wave background that satisfies delta and effective, what strain must it have? 5 orders of magnitude lower than where we're going to be at a megahertz. So that's disappointing, but that's where we're at the moment. What could these instruments then hope to see? Well, it would have to be a late time signal of these gravitational waves. Just to give you some intuition, LIGO saw roughly 10 solar mass.
Wouldn't the gravitational wave from inflation be higher than this?
Possibly. I guess it depends. Well, higher than the delta and effective, you're saying?
The 10 to the minus 22, because, well, sorry, maybe not higher than that, but as you go to lower frequencies, it rises, the amplitude rises.
But the delta and effective bound also, I'll show you in a plot later on, also rises as we go to high frequencies. So maybe what's a little bit misleading about this is that we're looking at strain rather than energy density. The energy density in the gravitational wave is proportional to the strain squared. So sometimes people plot on energy density. For whatever reason, the high frequency gravitational wave literature is coalesced around strain, maybe because it looks a bit more impressive here. Actually, I think anything that's coming from the early universe, including inflation, has to be subject to this. At lower frequencies, it absolutely can have larger strains. If that's your point, I agree. And I'll show you what this delta and effective line looks like in a plot. Just to finish the discussion of what you might actually be able to see at this, recall that LIGO saw roughly 10 solar mass black holes at a frequency of about 100 hertz. So you want to use a black hole to produce a signal at maybe 100 megahertz. You have to go up 6 orders of magnitude in frequency. You have to go down 6 orders of magnitude in the black hole mass, so about 10 to the minus 5. These are not conventional black holes. They would have to be primordial black holes you're looking for. So an exotic signal, one that could show up nonetheless. Now let me say a few words about what you actually have to do to compute the detectability of the gravitational waves more accurately, rather than this very tilde argument I gave you previously. You have to figure out what modification to Maxwell's equations does a gravitational wave induce. What we're able to show is you can write it in this form here. It gives an effective charge and also 2 terms that behave like an effective current, both of which can be written in terms of a polarization and a magnetization vector that I'm showing you here. Just to say, you can actually write the axion in the exact same language. It has this much simplified form I'm showing you down here, but of course it's not shocking that the gravitational wave is a more complicated interaction. While this may seem complicated, if you've thought about gravitational waves for a while, After staring at this expression for a bit, you might say, aha, I see a very clear way to simplify the equations I need to solve. If I move to the transverse traceless gauge, as we conventionally think about gravitational waves in, then these trace terms vanish, and also there'll be no time component. Actually, every term in this expression, except for the first one of these, vanish. That seems like a dramatic simplification. However, it is a deceptive one. It's a point that maybe it had been appreciated in some aspects for a while, I think was really beautifully emphasized in this very nice paper by Asher Berlin, Bastian Ellis, who's sitting in the audience, and his collaborators late last year. They said that, yes, these equations appear to simplify if you move to the transverse traceless gauge. You must remember that, of course, a choice of gauge in general relativity is also a choice of reference frame. What do you even mean by E and B when you're in the transverse traceless frame? It's not particularly clear, and it's quite complicated to determine. So, of course, if I'm working in the inertial reference frame of the laboratory, I know what I mean. I have a toroidal magnetic field or a solenoidal magnetic field. It's very clear to describe that. The transformation is not straightforward, and unfortunately, people have been led into error, sometimes mixing the two cases, like describing the magnetic field in the rest frame of, or the inertial frame of the detector, working with the gravitational wave in the TT frame, and of course, that's not consistent. So what ultimately was advocated by Berlin, Sebastian, and their collaborators is that while this expression is more complicated, ultimately it really is easier to work in the inertial reference frame of the detector, such that I know at least what the electric and magnetic fields are. I'll just have to deal with these additional terms, and the complication of exactly the gravitational wave won't be as simple as it is in the proper detector, as it is in the TT frame, sorry. For example, one of the results you find from this, that when you work in the proper detector frame, the gravitational wave, first gauge invariant contribution you get from this is frequency squared. As there are people in the literature who had thought there was a linear term in frequency you could get because they'd been mixing these two gauges. So let me just say a few more words about this. I thought it was quite an interesting aspect of the calculation. So again, if you're working in the TT gauge, up to the terms that describe the polarization, the gravitational wave is very simple. It's literally just a plane wave. If you expanded this out, you can see why people thought there might be a linear term in frequency there. When you move to the proper detector frame, in addition to the polarization and magnetization being more complicated, the gravitational wave itself is more complicated. We were able to get it down to this simplified form that I'm showing you here. It started out a lot messier. However, to draw your attention to the point that I made on the previous slide, you expand these terms out at leading order and frequency, every single one of them goes as frequency squared. If there's interest, I'm happy to say some words about why exactly that is, but this turns out to be a useful parameter to carry as we move forward to the detection. Now let me tell you about what would happen if our toroidal magnetic field ran into one of these high frequency gravitational waves. Now we do not have dark matter oscillating through the experiment. We have this gravitational wave. And whereas previously the axion induced this current that was proportional to the magnetic field, gravitational wave induces a current in every possible direction. For example, if you're working in cylindrical coordinates, I think I put the J rho the wrong way around, but regardless, it turns out if you want to compute the flux that will be induced in the center of this torus here, JZ component isn't required, but it is actually non-zero. So all possible contributions are there. Nonetheless, you can push through the calculation. You find parametrically that the gravitational wave does deposit a flux. It has the form that I'm showing you parametrically on the right-hand side here. So let's compare this sensitivity to what we had for the axion. The axion, the flux that we had was proportional to GA gamma times A. The one frequency that comes from the derivative because the axion's a pseudo-Goldstone boson, and there was a magnetic field and a volume. The gravitational wave, if frequency cubed, the analog of GA gamma times A is played by H. The magnetic field enters the same way. And we have a faster volume scaling because we need to make up the dimensions from the additional powers of frequency that's here. So it's great that you get a response. The surprise that I had when I did this calculation for the first time is why isn't the response proportional to frequency squared? I just made this whole song and dance about how at leading order, the gauge invariant contribution is frequency squared. Did the calculation, I got frequency cubed. It turns out there is a frequency squared contribution. You can look at what it is. It's actually sinusoidal around the loop here. So by using a circular pickup loop, that contribution integrated to zero. However, once you appreciate this, you can imagine making a minor correction to the way that you're reading out the flux. And if you use a figure-8 pickup loop, which I've attempted to draw here, it will show that you can actually exactly recover this second order and frequency scaling for the gravitational wave, which is the leading order contribution you should get for this. having told you what the sensitivity is, now let me just take what I know about dark matter radio and project that into a strain sensitivity here. Recall when I lied to you and I did this very rough estimate, I said things would be about 10 to the minus 22. Unfortunately, that was slightly optimistic. When you look at this, the future dark matter radio program will be able to reach the pink region that I'm showing you here. People have discussed larger versions of dark matter radio in the literature. If they were realized, you'd be able to get down here. You get a very, very good volume scaling for these gravitational waves, so this would improve dramatically. What I'm showing you is other various instruments that have been discussed. So for example, I focused on these low frequency instruments like dark matter radio today. If you'd like to understand how a gravitational wave interacted with a resonant cavity instrument like ADMX, well, this projection I'm taking from Sebastian and his collaborators' work, so that they figured out how that would operate up here. Then there are various other ideas that have been discussed, how you would detect high frequency gravitational waves. We cover some novel parameter space, and we're complementary in others. I think the point I would really emphasize about this is that many of these other detectors are dedicated gravitational wave instruments. What I'm telling you about here is a way to take an instrument we're already going to build for dark matter and get some gravitational wave sensitivity to it. You can also sit down and calculate what strain sensitivity would I need to achieve to see in the most optimistic scenarios a primordial black hole binary inspiral at a rate of about 1 per year. If you did this calculation, you find you have to have a sensitivity around this purple line that I'm showing you. Even this, if you were to see a primordial black hole binary signal, you would need to get quite lucky. 1 per year is not going to be enough to see this.
And effect, it will be here, like way down.
Great question, Nico. You've preempted my next slide. So what I'm showing you here is sort of the zoom in for what we have for sensitivity. Now let me zoom out and show you what's happening in the strain sensitivity more broadly. Firstly, exactly as Nico said, ultra ineffective is there. It's just well below the plot that I showed you. Just to emphasize, what I've done here is not just zoom out in strain, I also zoomed out in frequencies. I'm showing you a number of other proposals that were shown here. And indeed, because of the relationship between strain and energy density in the gravitational wave is proportional to h squared, as you move to lower frequencies, the delta N effective bound becomes less constraining in this space, which I think goes to the question I got earlier about how if you had some early universe signal, how could you see it, the sort of strains people are proposing? Could you just have to look at lower frequencies? What I'm also showing you here, though, are the joys that you would be able to realize if you could have an idea that got below these delta N effective bounds. You'd be able to see gravitational waves from early universe phase transitions, which should live somewhere within this band I'm showing you here. Potentially even the gravitational waves produced non-thermally from the early plasma, which has been calculated to look something like this, which depends upon the max reheat temperature of the universe. If you stare at this plot for a moment or two, I think there's one candidate that's being discussed that really draws my attention. And that is this one, the Lee-Baker proposal. No other idea gets anywhere near the delta N effective bound, but Lee-Baker gets below it. What is happening there?
Sorry, can you just clarify? The delta N effective bound should I literally be saying that because firstly, is this CMB stage 4 or the current delta N effective?
Current delta N effective bound.
So given the current delta N effective bound, is any signal above that line even possible?
Okay, yeah, good. Things to say. So definitely yes. Even if it's early universe, just one thing to note, the integrated energy density that the delta. So you can have, like, if you have a very sharp distribution, it can peak up a bit from this, but you can only play that game so long. The other thing to note, I mean, especially because relativistic distributions tend to be broad, so it's a challenging game to play, but one you can do. However, this is a bound set either from Big Bang nucleosynthesis or our measurements of the cosmic microwave background. If these gravitational waves were produced later on and nearby, of course you can evade this. And that's what I showed you with, for example, the primordial black hole.
But this dashed line was computed assuming a flat frequency distribution, presumably. Or,
I think it,
or log flat or something. Like.
I believe log flat. Yeah, I think that's right. Thank you, David.
Okay, all right, thank you.
Oh, good. Okay, so let me come back to the punchline. What's happening with Lee-Baker?
Would you say the ones produced from inflation are just below this graph, or?
I'm actually not sure off the top of my head. Nico is nodding, so possibly they are. So they may even be below this. Again, anything produced in the early universe, what I'm telling you here is that you would hope that it was also produced at lower frequencies, because then it would be a lot easier to see. However, there are some signals that are only going to be produced at high frequencies, like this cosmic gravitational background. Also, high temperature phase transitions would peak in this range. Well, again, this is just an envelope of the allowed things. The actual distribution would peak somewhat coming up to this green band. It's a good question. I don't know off the top of my head what the inflation is, but I believe from what the nodding I saw that it's below the point. So back to Lee-Baker. So actually, our current understanding of the Lee-Baker result comes to us courtesy of the US Defense Force. So Lee Baker was such a sensitive proposal, there was actually a Jason report commissioned because there was general fear within the government that you could now use high frequency gravitational waves, both detect nuclear submarines and also communicate with nuclear submarines. This sort of led to the mother of all comment papers, where the Jason report concluded that they did many things incorrect, also said that there is no foreign threat from high frequency gravitational waves. And as far as they could tell, there was no practical use for them. I take a little offense to that, but okay. So let's take Lee Baker out of this plot here and say that the proposals that, as far as I'm aware, are correct are the ones that I'm showing here, and they're not yet getting to the delta N effective bound.
Hold on. So if you do have something which will go down to the N effective, that basically means that it can have practical applications.
I imagine that any instrument that would do this, right? For example, the future versions of dark matter radio, like the orange ones I'm showing you here, are the size of CMS. So even if you could, you need to put an instrument like that inside your nuclear submarine, right? So, but I mean, again, this would require maybe hundreds of years of technologies. Who knows?
Dark matter radio is the size of CMS, or dark matter radio 100?
Dark matter radio 100 will be the size of CMS. Thank you. Let me just end by saying that while I think this is an interesting possibility, realistically, what we would see is some rare event that we got lucky to come in, or potentially some source that we haven't anticipated yet. But definitely they should do these searches, but to get to where we really want this seems a bit challenging. Let me just end with a couple of words about why I think the detections up here are so challenging. These are very qualitative, but I think have at least helped my intuition. This is again to draw this line I told you about earlier on, and I made this distinction about gas-like dark matter and wave-like dark matter, the same for the CAB. I can draw the same curve for the gravitational wave background. And it turns out that if you live below this plot I'm showing you here, you do not have a gravitational wave, you have a gas of graviton. So if you want to make a detection down here, what you really need to do is detect an individual graviton. This is a very challenging enterprise. I think, as was, for me, most beautifully encapsulated in this paper by Dyson, I think was the last thing he wrote, which is a graviton detectable? He runs through a number of very thoughtful ideas, concludes that while he can't physically prove you can't detect a graviton, he concludes with any idea he can come up with, there seems to be no hope of doing so. I've just been rethinking this question recently. I can say one caveat that Dyson didn't think about is sort of exotic sources of gravitational waves, like primordial black holes. If you start to include these, the prospects become a bit better, still very challenging. So while I can maybe envision a scenario where you could see one graviton from these sorts of events, actually doing anything particularly useful with this still seems exceptionally challenging.
What about the experiment across the line?
Good. So if they were to see something, they would actually be seeing an individual graviton in some sense. It's a very good question. So CAST is sitting down here. Again, remember, how does CAST operate? It converts an individual quanta into a photon that you see. That's what it's doing with axions. The claim would be a graviton that passes into that magnetic field converts to a photon that we then detect. You can ask one question that my collaborator Dan Carney is an expert on, and we've been thinking about a little bit. If you actually started to see some clicks from of these gravitons coming in, you actually start to answer questions like the source that produced it is really behaving quantum mechanically. But actually, as is known in the quantum optics literature, this is impossible here. You need a very, very efficient detector. A computed CAST is, the efficiency of CAST to detect gravitational wave is about 10 to the minus 36. That will not cut it for saying really interesting things about here.
CAST, you say, was decommissioned? Or what
CAST has been decommissioned. Yes, there was a party recently at CERN to celebrate that. But there are future versions like IAXO, which will go forward. Indeed, it has a slightly better sensitivity, I'm showing you here. So with that, let me step back and say that where we really want to go is some way off. At the moment, these instruments we're building to look for axion dark matter really can operate like high-frequency gravitational telescopes. Then let me step back once more and remind you, I think ultimately the takeaway I hope you have from this talk is that this is a very exciting time in the search for dark matter. New dark matter is made of an axion. The ideas for how to detect it have really started to take shape. In the coming decades, we'll cover so much parameter space that we really might be in a position to finally resolve this mystery of dark matter. Additionally, what I've also tried to tell you about today, you can do more with these instruments than just look for dark matter. Maybe you've been left with an even further reason to be excited about where this program is going. Okay, with that, I'll end there, and thank you so much for your attention.
Give us an idea of what the scale of these proposed dark matter radio experiments are. Scale and size and dollars and.
So, oh, this is getting political. So as I said, this biggest version that's ever been discussed is about the size of CMS.
I think
CMS is, oh my goodness, 20 meters wide or something like this. I'm embarrassing myself here. But it's order tens of meters wide and many tens of meters high, for example. This is a very large instrument that takes up an enormous room, for example. However, we built magnets of that size before, so it's not completely nuts. But I do think you are getting into the regime where it's hundreds of millions of dollars or many hundreds of millions of dollars. Not getting to the billions, but hundreds of millions, which will be required. And to say where we are as a field at the moment, the prototype experiments have been improved. I'm not sure if I really made this super clear, but this envelope I'm showing you here is actually made up of 3 different instruments. It's going to be dark matter radio 50 liter, which is the volume. Then there'll be dark matter radio meter cubed, which is a 1 meter cubed instrument. And there's going to be dark matter radio gut, because it gets down to the gut decay constants that are associated with these low mass axions. And gut, I think, is several meters wide and high. That will probably cost several $100 million. Give you something to
Also, dark matter radio 100 is more.
Yes, it's what this technically is. It's not 100 meter cubed. It's 100 meter cubed of magnetic field volume. So it ends up being about the size of CMS. I should know better, but it's tens of meters.
So just to tack onto that, does dark matter, is it just a matter of building a bigger magnet, or do you need this? Do you need very fancy materials for shielding this thing? Which
100%, yes. Yeah. Like to just give some. I mean, not to be dismissive. It's an excellent question, but definitely the noise sources are going to be very challenging. When I made this statement earlier, let me be honest, we have achieved with Abracadabra the theoretically predicted noise floor over a frequency range, not everywhere we look. There were several places where there remain backgrounds that we have not yet been able to isolate, and they must remove. Because remember that, I mean, where Abracadabra was operating is above the plot here, so we need to do much better. So to give you a flavor of the type of things that picked up, of course, any vibrational noises can create aspects in the frequency range we're looking at. Even various radio signals you pick up in these. You definitely need to shield it, absolutely.
Indeed, I wanted to ask you about the background of those signals. So what are the different backgrounds and how do you get rid of them?
So, I mean, there's many different background sources, some of which I already mentioned. Generically, you need to exceptionally well vibrationally isolate this system, because anything in that that causes your system to vibrate will cause stray magnetic fields that will go into that pickup loop, and you could potentially read out a background. So often what they will do is they will hang this off a spring like this dilution refrigerator, because you need this to operate at very low temperatures because the magnetic fields are produced by superconducting currents. So you're hanging some dilution refrigerator off a spring in order to make it vibrationally isolated. This is one aspect you need. Even then, there are other electromagnetic waves definitely will produce a response when they pass through. So for example, various radio signals that worry about. That's just, I mean, this you need very, very good shielding. And I mean, this is just a subset of all the possibilities. There's a lot more that can be said about that.
Yeah, so then I'm going to ask my question that we talked about.
Yeah.
With VM radio, looking for a linear.
Absolutely.
No. And although it may be a sum of waves, at least one can include that in the analysis. But what would be the type of source that will produce? Yeah, first of all, how big a signal does one need? How coherent does it need to be? And what would be a potential source for these kind of signals?
So this is a wonderful question that I probably, it would be unfair to do full justice to it. But let me say a few words I can say on this. So there are two different notions of coherence. There's the classical notion of coherence, which is a measure of how wide in the frequency domain is this distribution. This is not at all the one we're discussing here, because we know how coherent dark matter should be. This just follows from our knowledge of its speed. Instead, the coherence you're referring to is as like a system of a quantum state. How exactly do I believe that the dark matter is distributed in the energy levels at a given K mode? Right. So everything that is done in the literature in this topic, to my knowledge, though I haven't dug into it completely, people assume that the dark matter is in a coherent state. And it's when it's in a coherent state and the degree to which it's in a coherent state, that all of these conclusions follow. If there are deviations from a coherent state, I'm not aware of anyone particularly figuring out exactly what would happen to dark matter. But the usual assumption is if you have very large occupation numbers, the coherent state is a very accurate description.
The physical mechanism that would put the
Well, the easiest way to describe this is that we think that the axion is produced from misalignment. So that seems like a very reasonable way of generating a coherent state, for example. But we don't know for certain how the axion was generated in the early universe. If it was not misalignment, it's not immediately obvious to me why it has to be in a coherent state. For example, we know that the thermal distribution is not in a coherent state. How exactly did that coherent state picture emerge? I actually can't tell you honestly. It's something I'm quite interested in and thinking about at the moment. It's a very, very good question.
Okay, one question here. So supposing you have a signal with these instruments, is it going to be easy to say to tell about which scenario this is the gravitational-wave and axion?
Good. Yeah. So if it's dark matter, it actually will not be that hard to do because we know we have so many properties of dark matter that we understand. Something that I was thinking about recently, and I think this would really be a slam dunk for these types of ideas. If you start to see a signal, all right, you've already spent several $100 million building one of these instruments, build a second one, I can calculate exactly where you should put it. Because this is a literally a wave, I can perform interferometry on the wave. I know which direction dark matter is passing through the Earth. With two instruments, I can exactly predict what is the interference pattern between the two instruments that would be produced for dark matter. It is a deeply non-trivial property of dark matter that I think very rapidly allow us to confirm that that's what we're seeing. In fact, with the simulations we had, if haystack, for example, for a signal, what you could do is you could build a second haystack, put it 1 meter away. I can calculate exactly the optimal place to put it. And then with 1 day of data, it would be able to predict where the signal is coming from on the sky within a degree accuracy. We know where it's coming from. It should be coming from the Cygnus constellation because of our movement through the halo of dark matter. So that is how we would, dark matter case, that's a lot easier. That's why I said the most about it. These other cases are a bit more challenging. Of course, they're not expected to show up like dark matter. Being relativistic, you should see a signal over a broad range of frequencies. Exactly how you would tease these apart in like the specific case from, do you initially see a cosmic string or a Gaussian that was peaked around here? You have to collect more data to map out the shape. You would, however, be able to distinguish a gravitational wave and a relativistic axion, because the gravitational wave depends on the incident direction of the object. And there's also dependence upon which polarization is interacting. So for example, throughout the day, the gravitational wave signal would change non-trivially. But I mean, throughout the day, it depends how long this signal lasted, for example. You have tools in principle. In general, it could be complicated, but there are certainly tools available to do that. Good question. Thanks.
Okay, so thank you for the
Thanks, everyone. Oh, okay.